So this is the heat equation where we're going to look at the heat equation on a ring. So here the setup is we have a thin wire that's bent into the shape of a circle, and it's connected at the ends. So using the power of the mind, we've taken, we've taken the metal rod now, and it's a very thin metal rod, right? And now we've bent it so that its ends are touching. And so, those are the ends right there. And so now we'll get certain types of boundary conditions. So let me talk about the geometry here. So we are calling this x equal to negative L, and then this would be x equal to 0, and then when you're all the way back around, so x equal to negative L, so we're all the way back around here, we're at x equal to L, and the circumference here is 2L. So the circumference we calculate as L minus L. We're really still thinking of it as an interval, basically. But now, we're pretending that this end, like a torus, just loops back to this end. And then it just keeps looping around. So we're still essentially treating it like an interval, but it has this, we've given it a periodic property. Basically, what we've done is a type of extension of the interval. We've taken the original interval minus L to L, and now we're pretending like it just keeps repeating. So now this is again here, it starts again minus L to L, and it just keeps repeating forever and ever. Or, think of it as a thin circular ring. So we assume that the temperature, I don't know, there's a plane flying overhead. I don't know if you can hear that, my apologies. I scheduled it to be a no-fly zone today, but no one listens to me. So the cross section of the metal, we assume that, for this 1D model that here, the temperature is constant across the cross section. We're only expecting temperature variation along the thin wire. So maybe one portion might be hotter than another portion. So here is the PDE. So I need to motivate these boundary conditions. Okay, so for now, if you're like, wait, what's up with those boundary conditions? So hold on, So these boundary conditions are sometimes known as perfect thermal contact, which I'll talk about here in a second. So as always, heat equation is standard. So here, think about the domain, minus L to L. And you should think back to when we started this course, when we weren't even doing any PDEs, we were just studying the technical aspect of Fourier series. We were looking at Fourier series. The Fourier series we know and we got used to were defined on minus L to L. And so we've come, in some sense, we've come full circle here. Full circle, like something that's round. I can't think of anything that's round, but anyway, so we've come back, to being on the domain minus L to L. So here are the boundary conditions. Just from a mathematical point of view, this is, we're just saying that the function u at negative L and L are identical, and the derivatives are as well. From a physical point of view, this is what we call the perfect thermal contact assumption here. We're assuming perfect thermal contact at the ends. And so what does that mean? Well, we're assuming the temperature is continuous at the ends. And so that's this assumption right here, that the temperature at negative L and L are the same. The temperature is continuous. And also the heat flux is assumed to be continuous. So our other assumption is the heat flux is assumed continuous at the ends. So how do we, how does that get us here? Remember that we have Fourier's law. And so Fourier's law says the heat flux is proportional to the spatial temperature difference. Here, what we're saying is that phi, so phi itself is a function of x and t, right? So here we're saying phi of negative L comma t equals phi at capital L comma t. And then when you cancel the negative k sub zeros, there, I got away with my writing for today. Yes, got to practice every day. So when you cancel the negative k sub zeros, you end up with this equation. So, accept it mathematically, accept it physically, however you think about it. For me, unfortunately, when I originally started studying this material, I approach it from a very technical point of view. So for me, they're just mathematical boundary conditions, and then, of course, we have our initial temperature. So here at time t equal to 0, we have our temperature distribution. All right, folks. So, if we kind of take a moment here to reflect, think about when we solved the heat equation and we only had, for example, these type of Dirichlet boundary conditions where you had u at 0 equals 0 and u at capital L equal to 0. When we had those kinds of boundary conditions, we ended up with a Fourier sine series. And when we did the problem where we had, these boundary conditions that were of this Neumann type, we had partial u at 0 equals 0, partial u, partial x at L equal to 0. When we did that problem, we got a Fourier cosine series. So now we have both of these kinds of conditions. I hope you see where I'm going with this. We're going to now get, these conditions are going to result in a full, Fourier series with both the sine and cosine terms. Okay, and so here we're expecting to see the full-on Fourier series that we studied at the beginning of this class, defined on minus L to L. So remember, when we did the Dirichlet boundary conditions, we got this Fourier sine series, and we did the Neumann boundary conditions, we got this Fourier cosine series, and now we're going to see both terms will make an appearance. So one other thing here is I'm going to solve for R, because this will come up in our calculations later. So I want to solve for R in terms of capital L. Okay, so it'll seem kind of random right now, but it'll come up later. So the circumference of the ring is 2 pi R, and the length of the wire, which goes from minus L to L, the length of the wire is 2L. So we've got circumference of the ring, and then compare that to the length of the wire. And so we set those equal to each other and solve for R. And so I have R equals L over pi. So this is just right now, we will use this information a little bit later. Okay, so we'll put that in our back pocket for now. So one other thing here is with the ring, we can actually define the domain for X here to be all real numbers, because we can essentially, say that there's a periodicity here in the X variable. So again, I want you to be very specific. In PDEs, we have the X variable and the T variable. So here on the ring, every time you go a length of 2L circumference, you're back where you started, right? So here we have, if I'm at some point and then I travel along the ring, a length of 2L, I'll be right back where I started. So here we have this periodicity, additional periodicity assumption on the spatial variable of the U function, the temperature. And so we can think of this as actually being defined. Here, we say it's from minus L to L, but by, doing this periodic extension, you can also think of it as being X as any real number. So, all right. We're going to solve this PDE. And, here's the the thing I always say to you is I say the set of functions that satisfy the PDE and boundary conditions, if the set of functions that satisfy the PDEs and boundary conditions form a vector space, we can immediately start doing separation of variables. So if we go back here and take a look, I'll let you verify this, but here, the set of functions that satisfy these boundary conditions, the PDE and the boundary conditions form a vector space. Let's review. What does that mean? That means if U1 and U2, not the band, if U1 and U2 satisfy the PDE, then if you add them, they also satisfy the PDE. If U1 and U2 satisfy the boundary conditions, then if you add U1 plus U2, call that U3, then U3 will satisfy the boundary conditions. If U satisfies the PDE and you take U and multiply it by a constant, call that a new function, C times U, that will satisfy the PDE. If U satisfies the boundary condition, you take U and multiply it by a constant, that new function will also satisfy the boundary conditions. So let's review what that actually means to say the set of functions that satisfy the PDE and boundary conditions form a vector space. So here that is the case. I'll let you verify that. And so we don't have to do transient and steady state. We don't have to break it up into U bar plus V. In this case, we can do separation of variables directly on the variable U because the set of functions that satisfy the PDE and boundary conditions form a vector space. So now I'm going to assume U equals F times, U of xt equals F of X times G of T, and that they're non-trivial. And you know how this goes? We're going to plug it into the PDE. And then using the fact that one function is a function of X only and the other function is a function of T only, we can separate the, we can separate the equation and have a function of T only on one side, function of X only on one side. And then you can prove that the only way this is possible if they're both equal to a constant. And so we call that constant negative lambda for convenience. And now we need boundary conditions. So here, this part's slightly different from what we've done in the past. Here we have these type of, perfect thermal contact boundary conditions. So here we say U of negative L comma T equals U of capital L comma T. I'm replacing, right? I'm using this assumption right here that U equals F of X times G of T, and I'm plugging in, capital negative L for X and then G of T. And so then we're doing the same thing on the other side using this equation here to get that side. And then I cancel G of T. So now we can equate, so cancel, cancel. And so now I've got a boundary condition here on F. And we do the same thing with the derivative, because the other boundary condition is partial U partial X at negative L equals partial U partial X at L. So the heat flux is continuous. The temperature is continuous at the ends where they touch the, and the heat flux is continuous. And so that translates to, that's an X derivative. So that gives us an F prime here. And so you get F prime of negative L equals F prime of L. And so now we can assemble our time domain problem and our eigenvalue problem or T variable problem and X variable problem. And the time domain problem is the same as always. It's what we know and love. The eigenvalue problem, this part's the same, but here now we have these new boundary conditions resulting from that, so-called perfect thermal contact of the ring that we've connected at the ends. Using the ODE technique of separation of variables, we can show that the solution of the time domain problem is this exponential function c times e to the minus lambda kt, where this lambda is what links it up to the time domain problem, right? To the, boundary value problem, the eigenvalue problem. So we're going to solve the eigenvalue problem now to find lambda and then do a product solution and combine everything. So for the eigenvalue problem, I actually worked out the case lambda less than 0. I mean, just in time for after you did the homework. Sorry, I maybe should have done it earlier. So here, actually it was on purpose. So here, I'm assuming lambda is less than 0. So I'm going to just go ahead and write lambda as negative m squared for some non-zero m. So here, so negative m squared here will always be negative. And so in the characteristic equation, I replace, negative lambda, if you multiply by minus, so that becomes m squared. And then I take a square root, so I get r equals plus minus m, and then this r gets plugged in up here into the e to the rx. And so then I get, then you take a linear combination. So here's my general solution. That's a linear combination of e to the mx and e to the minus mx, where lambda equals, here we're assuming lambda is negative, so I've written it as negative m squared. And so now I'll show you the boundary conditions imply the only way this works is if C1 and C2 are 0. So the first boundary condition, f of negative L equals f of L. So what we're doing is we're replacing the x right here with negative L, and then equating that to the same thing, but replace it with L. So on the one side, I'll have c to the m times negative L, C1 times e raised to the m times negative L plus C2 times e raised to the m times L is equal to, so that's when you plug in a negative L. So the negative and the negative cancel. So here, this is just L, because here, the two negatives cancel when you plug in a minus L. So right here, we'd have a minus L, and then, minus minus. So there's a minus sign right there. And on the other side, we've just replaced x with L, set them equal to each other. And so here, I collect all the terms that are multiplied to e to the minus ml together. So move everything over. Move this over, move this over. Those terms, get a minus sign in front of them. And then collect all the constants that are being multiplied to the same exponential function. So C1 minus C2 times e to the minus ml plus C2 minus C1 e to the ml is equal to 0. And so I do the same thing with the other boundary condition. So you take the derivative, remember here, derivative e to the mx is m e to the mx. And here we get the minus sign, we take a derivative. And again, plug in negative L and set them equal to each other. And what I do is I cancel the m's. M is not 0, m is non-zero, and it's appearing on both sides in every term. Cancel the m's, and then bring everything over. Bring all the terms over. Collect the like terms, everything that's multiplied by e to the minus ml, put those together and factor out the e to the minus ml. Everything that's multiplied by e to the ml, put those together, factor out the e to the ml. We get this expression here. And so now I'm going to add these two equations that we got. And there's probably more than one way to do this. I'm not necessarily sure this is necessarily the most efficient way. And you add these two equations together and see what happens. So when we add the two equations, certain parts cancel out. So let's see here. This negative C2 e to the minus ml. So let me use a different color. This term right here will cancel. The negative c2 e to the minus ml will cancel with the plus c2 e to the minus ml. The c1 e to the minus ml will double up. I'll get 2 c1 e to the minus ml. And over here on the other side, let's see what cancels here. The c2 here will cancel with this minus c2. And so add those and you get this equation right here. So here's the double up of that term and the other term right here. Sorry, those are the terms that get canceled out. These are the terms that get doubled up. Here we go. This term here, minus C1, got doubled up. And the C1 term here. All the other stuff gets canceled out, right? So this is gone, this is gone, this is gone, and this term's gone. So now I factor out the C1 and cancel the 2's. So cancel the 2 and cancel, factor out to cancel 2 on both sides here. Just cancel, factor it out and cancel it, or divide both sides by 2, however you want to think about it. And then factor out the C sub 1. And then I added this detail last night and uploaded the slides. It was a bit late, my apologies. Here, this is an easy way to think about it, is that e to the minus ml minus e to the ml, that's actually the same as negative 2 sinh ml. Remember that sinh of x is e to the x minus e to the minus x over 2. And so here we have, if you look at this term here, that's the opposite. Here, that's negative e to the x plus e to the minus x. It's the negative of sinh, and it's missing the divided by 2. So why did I bring sinh into it? Because if you look at the graph of sinh, the hyperbolic sign is 0 at only 1 point. So the graph of sinh kind of looks something like this. Whoops. The graph of sinh kind of looks like this. And so you see sinh is only 0 at 1 point, at 0. So here, if sinh of blah equals 0, the blah has to be 0. So here, m times L is not 0. That's what we know. We know for sure m is some number. It's, because this is the case lambda is less than 0. So m is not 0, and L is the length of the rod, presumably not 0. So here, that term, that sinh of some non-zero number, that term's not 0. So what I can do is I can divide both sides by this non-zero term and conclude that C1 equals 0. And so now you take this assumption and plug it in here, then our solution now looks like, well, C1 is 0, so our solution just only looks like C2 times e to the minus x. Again, if you apply the boundary conditions, you can again end up with an equation like this, but involving C2. You can play the same trick by using the boundary conditions. And so we can prove that C2 is also equal to 0. We get a trivial solution. And this is why, in this case, we don't look at the case lambda less than 0. I can't say across the board for every PDE lambda less than 0 is not going to be a solution, but here specifically for the heat equation, for these boundary conditions that we've studied, it hasn't been a factor, So it's always possible that it could be. It's just that in this case, it isn't. For lambda equal to 0, we've done this before. You just go back to the original problem, go back to the original ODE up here, and replace lambda with 0. You get this f double prime equals is 0, and just integrate twice. When you integrate the first time, you get a constant, call it a. When you integrate the second time, you get ax plus b. And so now when I apply the boundary conditions, so here, you know, f of negative L equals f of L, I'm plugging in, I'm replacing x with negative L and L in the equation ax plus b and setting them equal to each other. Here, the b's cancel, the L's cancel. You end up with the equation negative A equals A. Bring the negative A over, you get the equation 2A equals 0. And so then we get A equals 0. And then, so our solution now looks like f of x is just a constant b. So this term here disappears. And the other boundary condition doesn't help us. The other boundary condition involves a derivative. When you take the derivative, the b term disappears. So the other boundary condition doesn't help. We say f prime of negative L. So here, if I put primes here, so the other boundary condition is f prime of negative L equals f of L. But f prime of x is just A. So the other boundary condition doesn't help at all. So we conclude that here lambda equal to 0 is an eigenvalue and it's equal to a constant. And so for lambda equal to 0, if you plug that into the time domain problem, the time domain problem is also a constant when lambda equals 0, because g equals c e to the minus lambda kt. If you replace lambda by 0, e to the 0 is just 1. So the product solution here, in the case lambda equal to 0, is f of just the product of two constants. It's just some constant. If you think about your full Fourier series, it has this constant term out in front, and so that's the term we've discovered here. So in the case lambda greater than 0, we do the usual stuff. We negative lambda will be the square root, the positive square root of negative lambda, if lambda is greater than 0, will be imaginary. And we use Euler's formula to find a linear combination that's cosine plus sine. Of course, you don't have to repeat this discussion every time when you're doing. It's okay for this case to go right to this step. You don't have to go through this whole discussion of Euler's formula, blah, blah, blah. I do it because I want the presentation to be complete. And I want to do it because I want to remind you, how did we get here? So now we apply the boundary conditions. We set, this function here, C1 cosine square root lambda x plus C2 sine square root lambda x. We replace the x with negative L on one side and L on the other. And so that's what you see here. You say on the one side, we've got x has been replaced by negative L. On the other side, x has just been replaced by L. So now let's use our geometry. Remember, cosine is an even function. So look right here, cosine of negative root lambda L, that's the same. This is an even function. Here, that's the same as being equal to C1 cosine of just root lambda L without the minus sign. So I made the minus sign go away there. And for the sine function, you remember it's an odd function. So over here with this function right here, that minus sign, we can actually pull it out. So because it's an odd function, this minus sign, I can take it from inside the sign and put it out in front here. So let me replace now this plus symbol with a minus. So you see what happens? The cosine terms cancel completely. And if you bring this minus C2 sine root lambda over, it doubles up and it's equal to 0. And that's the equation I have over here. using the fact that cosine is even and sine is odd. That's how we get there. So that implies either C2 is 0 or root lambda L equals n pi, because sine is 0 at the integer values of n. And here we've left off n equal to 0 because we already looked at, if n equals 0, then lambda equals 0. And we've already looked at the lambda equal to 0 case on the previous slide. The other boundary condition, when you take a derivative, think about what happens. Our cosines and sines flip-flop, and you get an extra root lambda outside. So here, this, what was a cosine before, has now become a negative sine down here in the derivative. And what was a sine before has now become, a cosine with that root lambda out in front. That's from taking the derivative. And then we plug in, the boundary conditions. So then we plug in the minus L part. And then same thing on the other side, except we plug in L. Let me review what happens again. We use the geometry again. Cosine is even. So we can make this minus sign disappear. Cosine of minus x equals cosine of x. Sine is odd. So this minus sign, I can pull it out. It cancels with this minus sign. So now if you look at it, the cosines will cancel. So here, this term cancels with this term. And these terms here, if you move this term over, it'll combine. It'll go from negative to positive, and we add it to the same term that's on the other side. So we're going to get 2c1 root lambda, sine of root lambda L equal to 0, and square root of lambda I canceled on both sides because it's not 0. So just cancel that. So we're back. We get the same conclusion. If you compare the two conclusions, we get the same conclusion, that either C1 is 0 or root lambda L equal to n pi. So now there's a little bit of logic here. Okay, so let's just use a little bit of logic. So I say what we can't have, and read this as a single statement, we can't have C1 be equal to 0 and C2 be equal. So read that as a single statement. We can't have both of those equations simultaneously be true. Otherwise, it would give us a trivial solution. If C1 and C2 are 0, F is 0, U of xt equals F times G, U would be 0. That violates our separation of variables assumption that we have a non-trivial solution. So the statement C1 is equal to 0 and C2 is equal to 0 is a false statement. So the opposite of this statement is true. So either C1 is not equal to 0 or C2 is not equal to 0 or both, or they're both not equal to 0. So the only possibility, so what we've basically said now is this isn't a possibility, because in both cases here, when we worked it out, we said either the constant is 0 or you have root lambda equals n pi. Well, we've proved that, only in one case can the constant be 0, but not the other case. So either C1 is 0 and C2 is not, or C2 is 0. And so in either case, we end up being able to conclude, that square root of lambda equals n pi over L. So it's a little bit subtle here, and it's about our separation of variables assumption that we have a non-trivial solution. It's not possible for both constants to be 0. And so in one case or the other, we end up concluding root lambda L equal to n pi. If C1 is 0, then C2 can't be 0, and so root lambda L has to equal n pi. And if C2 is equal to 0, then C1 can't be equal to 0, and root lambda L equal to n pi. So here, both equations eventually lead us to the same place, that square root of lambda equals n pi over L, or lambda equals n pi over L squared. And then we see that there's more than one eigenvalue. There's one for each value of n. And here, I've dropped the minus sign. So technically speaking, it should be n plus or minus 1 plus or minus 2. So cosine is an even function. So cosine of minus x equals cosine of x. So having n be plus and minus 1 is redundant. And I just want a linear independence, so I drop the minus ones. And sine is an odd function. So sine of negative x equals negative sine of x. So those are scalar multiples of each other. They're linearly dependent. And so again, it's redundant to have them both in there. So I drop the negative terms and only keep n equal to 1, 2, blah, blah, blah. I mean, if we wanted to be difficult or whatever, we could just use n equal to negative 1, negative 2. You don't have to. It's just we're choosing, it works and it looks nice. So remember that we now put it all together. We do a product solution where we've taken this thing, we've replaced square root lambda with n pi over L. So square root lambda would just be, this part without the square. And we've plugged it in right there. So I have, and then we're multiplying this whole thing by g of t. I'm multiplying this whole thing by, e to the minus lambda sub n kt, where the lambda sub n, again, I'm replacing this with n pi over L. Oh, this is lambda. So I'm actually, this will be squared, n pi over L squared. That's not square root lambda. That's just full on lambda. So, so then you get this thing right here, which looks like our, looks very familiar in terms of that standard Fourier series. So here's my product solution. I've multiplied the g of t time domain problem across the boundary value problem. Now, if you use superposition, we can add all the terms and get this huge mega solution. Alana, go ahead.
I was wondering why in the first case, which is lambda is less than 0, we end up with a trivial solution, but it doesn't violate the assumptions required for separation of variables.
It's not that it doesn't violate the assumptions. We just don't consider it as an eigenvalue because it's unproductive. It just doesn't work.
Okay.
So now when we do our big mega linear combination, you get this thing that we at the beginning of the class, introduced. Well, it's not a Fourier series. I always say that this is a Fourier series, but it's not a Fourier series, right? When you let t equal to 0, this will become what we called a Fourier series at the beginning of the class. When we let t equal to 0 now, the exponential terms disappear when you let t equal to 0. And so then we now get this mathematical object, which we defined at the beginning of the semester as a Fourier series. And now, we know all about this. We're not going to now learn about what's a Fourier series because that's kind of what the book does at this point. We already know now that these terms, 1 cosine pi x over L, sine pi x over L, cosine 2 pi x over L, we know that forms an orthogonal basis. And we know using the orthogonality and their projection formula, you can find the formulas for a sub 0, a sub n, and b sub n. And these are all things we worked on at the beginning of the semester with the orthogonality, and all of you did the integration by parts millions of times. So this is all stuff It's, now is the part you should try and take a step back a little bit and try and see the big picture. And here, we can do our large but finite time approximation. You know how we do a first term approximation. So here we include the a sub 0 term and the first term from the cosine part and the first term from the sine part. So that's what you have. Here's a sub 0. Here's the cosine part. Here's the sine part. And then the exponential function, it's the same on both terms, so I just factored it out. And what you should notice is, oh, here's the part that's got the x variable. And here's the part that's handling the t variable. The spatial behavior of the temperature versus the time behavior of the temperature. And those two components are, regulating that. And finally, we can check here that, does this have a steady state solution? Without solving the PDE, since we know the actual solution, we can just take the limit as t goes to infinity. So without going back and saying, oh, what's the steady state problem? And let me solve an ODE, blah, blah, blah. We have the solution. Let's just send t to infinity. When we send t to infinity, the exponential term, the time term, goes to 0. And so these terms, you say t to infinity, that goes to 0. We're only left with the a sub 0 term in the front. So here for the ring, the steady state temperature eventually should cool down to the average temperature. And to me, physically, that makes sense if you don't have any internal source of energy. So you heat the ring, right? We first take this metal rod, we dunk it in this super hot bath of liquid. We pull it out, we insulate the lateral sides. We then shape the metal rod into a ring and connect the ends so perfectly that we have perfect thermal contact. And then we walk away from it. Left to its own devices, eventually, imagine one end is hotter than the other. Eventually the temperature spreads out, evens out, smooths out, averages out. So kind of, it makes sense to me that the steady state solution here for the ring problem would be the average value. And so the formulas here now are slightly different because we're not integrating from 0 to L. Before the other PDEs, I kept warning you, hey, we're starting with a function that's defined on 0 to L, not negative L to L. Now we are on negative L to L. And the formulas are slightly different. But all the theory still implies, orthogonality, everything like that. So let me end here. I've got 5 minutes. Let me finish up with just a discussion of how the Fourier sine series, Fourier cosine series, and regular Fourier series related. So we have the Fourier sine series, the Fourier cosine series, and then the actual Fourier series. How are they related? So given a function, we can decompose the function in what we call the even part of the function and the odd part of the function. Be very careful. This is not the same as even extension or odd extension. That's why the notation is different here. This is the even part of the function, so it's the f sub e, and it's defined to be 1/2 f of x plus f minus x. So what's up with this weird definition? Well, this, if you can check, I'll let you check, this defines an even function. Okay, and we can define the odd part of the function to be f of x minus f of minus x divided by 2. That's known as the odd part of the function. And so what's that about? Well, the odd part of the function can be shown to be an odd function. So now what you should notice, if you take the odd part of the function and add it to the even part of the function, look what happens here when we do this sum. Here, f of negative x cancels with negative f of minus x. I end up getting 2f of x divided by 2. I get back the original function f. Okay, so the even and odd part is a way of decomposing any given function. It allows us to write any given function as the sum of an even function and an odd function. Okay, so Now, here's the connection between everything. Remember that a Fourier cosine series, we can only take the Fourier cosine series of an even function. So this first part of the Fourier series can be thought of a Fourier cosine series of the even part. So remember, we can only take a Fourier cosine series of an even function. So we can think of that part as the Fourier cosine series of the even part of f of x. So f of x, I have a way of decomposing f of x into an even function plus an odd function. Take the even function, find the Fourier cosine series of that, you get this. And the other part with the sine, that's the Fourier sine series of the odd part of the function. So you have a function, you can decompose it as a sum of an even function and an odd function. Take the odd function and find the Fourier sine series of that. You get this. So that's how all three of the Fourier series kind of relate to each other. And I'll show you, you can get the formulas for the Fourier cosine series or Fourier sine series from just the regular Fourier series. You know, I'll show you here in a second. So here, these terms should not be here. I'm sorry, these exponential terms should not be here. Because we're talking about the Fourier series, so this is like a typo. So these terms here, those shouldn't be there. Okay, so I'll fix that and repost it. Because we're just talking about the Fourier series. My apologies. There should be no time component. Okay. So yeah, sorry about that. I'll fix that and repost this. So I'm done here. The last couple of slides, which I'll go over next time, but the last couple of slides are just reviewing what we've talked about. So you've got your Dirichlet boundary conditions. So I want you to focus on the boundary conditions, Dirichlet boundary conditions, and then the type of solution we get. So in this case, Dirichlet boundary conditions and Fourier sine series. Here, look, this is 0 to L. Then we did these Neumann boundary conditions. Again, focus on the boundary conditions, the domain of X. Here, with these boundary conditions, we got Fourier cosine series. And then we did the ring problem today. So these boundary conditions are known as Cauchy boundary conditions. Look at the domain, look at the boundary conditions. In this case, we get a Fourier series involving cosine and sine terms. Okay, so, and then you can also have mixed boundary conditions. So here, look at this mixed boundary conditions. So if you look at the fall 2019 exam, there's a PDE with mixed boundary conditions on there. And so, you know, this might be a good example to review just for good practice. And here you get it's not a full-on sine series, it's the sine series, but only the odd terms. You know, so I'll let you look into the details of that. Also take a look at that fall 2019 exam I mentioned. So I'll finish this up next time. I wanted to put all of the Fourier series on one slide for you and then compare the formulas and show you how you can get one set of formulas from the other. And so I'll do that next time. And then I also did an example. So this example is very easy. I don't know if I'll go over it. I might go over it quickly next time, but then we'll also start the wave equation. All right, everybody. So we've officially kind of, you know, concluded our discussion of heat equation. And so we're going to next move on to wave equation, and we'll come back to separation of variables for wave equation. And, you know, of course, then we'll talk about convergence and all that good kind of stuff. Okay, so I'm going to stop right here.